conduct the attack. Let's start our attack. For tutorial purposes, we've put some of our commands into a run commands or run control file, or simply just RC file. We will use a Tomcat misconfiguration as our initial access method. For tutorial purposes, we'll upload some files at the beginning instead of toward the end, as attackers might actually do in reality. As attackers, we would normally start here by getting a shell. Next, we'll run a who am I. In this case, we see that we are root. This is not good news for the victim. Let's add a user for persistence. We'll double check that it got saved properly by looking at the password file. Looks good. Now, as attackers, let's do some extra reconnaissance with the getEntHosts command. One return host name in particular looks a little iffy. Wouldn't an enterprise name its hosts with something a little more reader or user-friendly? This does not look like a normal computer name. As perceptive attackers, this might make us start to think that perhaps we are in a container. Let's check the OS release. If this were run on a host machine, it would give us a different answer. So at this point, we have largely confirmed that we are running in a container. Let's run system control status. Nothing is returned here, so yes, we're in a container. Thus, let's start using the exploit. Our intention, now that we've realized that we are in a container, would normally be to get out of the shell, upload the files for our exploit, and then get back into the shell. But by having taken care of that earlier, by uploading it earlier, we don't have to do that now in the tutorial. Let's run the exploit. We can see that it worked because we got our second interpreter session. Let's exit and switch over to it. Our session has escaped the container, and we will see that now. We'll open up a shell, and we can see who am I? We are root, and we'll check the host name. Now this looks more like a real computer name with a normal naming convention of ERP-INV-10. Let's do a getEntHosts. Next we'll cat the etc OS release directory. We can check to see if the host has the same or similar architecture that the containerized system reported with a uname-r. As attackers, we want to be sure of exactly what we're dealing with, so we use the precise correct parameters. By running system control, we can see all the system processes running on the host machine itself. We can see that Docker is running. Let's type ps aux or aux. Now we see the Cybereason sensor. This confirms that the sensor is running on the host machine that is hosting all of the containers. As attackers, we have root access, and we can do pretty much any nefarious thing that we want to do. Cybereason has auto remediation via the custom rules feature. For example, if you found a container escape, you could automatically kill the process and or isolate that machine. Without Cybereason, this attacker has full access and could build Docker images, edit the valid Docker container images. This could be disastrous. For example, on the container that we just saw that was running Tomcat, as attackers, we could edit what applications that it holds. We could put a Bitcoin miner on there, or whatever we want. As attackers, let's add our persistence user to this host so that we can come back later or sell it on the dark net. We'll cat that directory, and we can see that we've successfully added our nefarious account and can now dump all of the passwords. This would be the credential theft and persistence phases. We could exfiltrate all of this data if we wanted to do so. We could take just a screen grab instead. We've seen where some of the critical assets are: machine names, passwords, users. We could drop some ransomware or do pretty much anything else we want at this point. We've seen one vulnerability, but you can see how any number of vulnerabilities in a containerized environment can lead to all phases of the kill chain or MITRE ATT&CK framework. In the future, there could well be a containerized Java application that has not yet been patched for Log4j, and IT professionals who mistakenly thought that its containerization rendered it secure are going to find out that they were sadly mistaken. Then, some new containerized escape vulnerability will come out, and everybody who thought that they were safe will wish that they had Cybereason's behavioral detection and auto-remediation via custom rules. Let's look at things from the defender's perspective. We're going to see the mallops which were triggered during the attack, and again, the Cybereason auto-remediation via the custom rule feature would provide the response or responses needed without the urgency for eyes on glass. Behind the scenes, we've acted as the attacker so that we now know roughly what happened and can now see from within the Cybereason's UI discovery board some mallops or malicious operations which we'll now explore. Let's navigate over to the mallops management screen. Here, we can see the activity that we just went through as attackers. So first you can see the web shell, and Cybereason tags it with the corresponding MITRE ATT&CK tactic. You'll recall that this was the Tomcat compromise. At the top of the screen, you can see the runc hijack container escape activity. Let's look at the container escape malop by clicking on it. Immediately, you can see the Cybereason suspicion of runc hijack and the MITRE tag of privilege escalation. The timeline shows the first execution, the resource affected, and the privilege escalation. Let's scroll down to the process profile section. We'll click on the attack tree icon and look at the execution chain. The suspicious process lineage starts with the dash process here, which is responsible for the container escape. Chronologically, we could scroll up slightly and note that the parent of this dash is Java, which is our containerized Tomcat application. Its child name, Dash, is the web shell that the attackers created on it when they used the exploit on Metasploit. In other words, this was our first Metasploit session. Let's click the plus icon to expand it. Here we can see the user ad that the attackers created for persistence. We can see the reconnaissance command. We can see the chmod on the binaries uploaded. With the cat, we can see the checking of the password files. In the details, we can see the particulars. We can see the main process, which is the process that enabled the exploit to happen. Pretty much everything in this part of the tree is that Tomcat container in the lower part of the attack tree. Then, as we change our field of view toward the upper part of the attack tree, we can see the container escape phase of the attack. This is a result of the container escape and the victim operating system being confused about what the parent process is. As defenders, though, we can see that this lower part of the tree is outside of the container context, whereas the top part represents the runc hijack. And we, as mentioned a moment ago, can see the child processes that represent what the attacker did. Recall that as attackers, we did similar things inside the container and then did things again when we were outside the container. And then at the cat, here's us checking the password file. Here's us adding a user, and here's us checking all of the running processes on the machine and the recon with the who am I. With Cybereason, we have full visibility, including all the processes that we ran as attackers both inside and outside the container. Remediation. Let's click the dash process. We can see the mallops details screen. We can click the response button, and for this tutorial, we suspended the machine that it was on, and thus the kill process option is grayed out, but normally you would be able to manually kill this process right here and isolate this machine to isolate it the next time it comes online and prevent it from spreading to other machines on the network. Investigation screen. When we navigate to the investigation screen, we can investigate or hunt for telemetry data in the containerized environments. We can click the See More button and search for the container element. Just to demonstrate here, we'll click the Get Results button, and we can see the container IDs in this environment. Let's extend our query structure by adding the process element and Get Results. You could extend the query structure to the things normally associated with the process element, as you would with our EDR product, such as services, scheduled tasks, requests, MSRPC, and registry entries in Windows, and so on. Here in our results, you can see that there are many suspicions and mallops. We can also see the different instance of the actual user add commands by hovering over the command line column. You can see that there's a container column here that tells us how many containers there are that are associated with that process name. The wget at the top, for instance, has 2 containers because it's been run on 2 separate containers, and we can see the owner machine or machines that are the hosts. Further, we can see the image file, which is the binary that the executable lives on. This shows that Cybereason is collecting, correlating, aggregating, enriching, and presenting container telemetry data and alerting us with the full story of the malicious operation in our mallops. Let's summarize. In sum, Cybereason distinguishes between containerized and non-containerized processes and reflects that in the telemetry data and provides you with the visibility into your containerized processes as well as visibility into their hosts. Further, it allows you to manually remediate or automate the killing of processes and isolations of machines based on custom detection rules which you can align with your organization's policies. The Cybereason platform provides the visibility, detection, and response solution to your cloud and cloud workload security issues. And Cybereason's Cloud Workload Protection, or CWP, optionally dovetails into the complete Cybereason EDR and XDR offerings.